Hello, everyone. It's my pleasure to be here to present you the science and data analysis with the TianQin Observatory. So today my talk will be composed with these basic components, some basics about TianQin and the TianQin astronomy and some summary. So what is TianQin? TianQin is a geocentric constellation to aim to use the laser interferometry to detect gravitational wave in space. The name for TianQin comes from the reason that Tian means heaven in Chinese and Qin means hub. So basically Tianqin is a hub in the sky that weighs the cosmic plunk of the gravitational wave. And for us astronomers, all we need to do from our colleagues doing experiments is this curve, or which boils down to these three parameters: the arm length, the acceleration noise, and the positional noise. So as long as we can have these parameters, we can predict what kind of astronomical sources we can detect and how accurately we can make the measurements. And this is exactly what we have been doing for the past few years. And our past few years' work can be boiled down to this diagram showing on the left-hand side. We can list all these possible different sources with TianQin and all the kind of interesting science we can do with these detections. And for the possible sources, actually, they are not very complicated. We can only expect to see several different kinds of binaries. And basically, they are two small objects or two big objects, or one small, one big. And let's look at the two smaller ones. These are the stellar mass compact binaries, which can be binary white dwarf systems or binary stellar mass black hole binaries. We know that there are a lot of binary white dwarfs in our Milky Way, and although there are only a limited number, 100 of them detected in the EM channel, but we expect to see a lot in the gravitational wave channel. Our study shows that with TianQin operation for 5 years, we can see about 10,000 of them, and we can measure them accurately. And for the foreground, which is indeed a big issue for LISA, actually this is not a severe issue for TianQin because of the slightly higher frequency for TianQin frequency band. And also, as we said, that we can be also sensitive to stellar mass black hole binary in spiral, while ground-based facilities can detect the merger as shown in the in this diagram, in the high frequency band. But in the lower frequency band, TianQin or LISA can detect the early in spiral, which can be used to perform the early warning. And we calculated both the detection rate as well as the parameter estimation precision. And we found that TianQin can detect them with high accuracy for different parameters. Now, let's move on to the massive black hole objects, the binary massive black holes. We know by astronomical observations that very massive black holes exist in our universe, and they are ubiquitous. So we see them in the center of our Milky Way and also in galaxies far, far away. And on the other hand, we know that the galaxies will merge. This is some observational evidence showing that the galaxies will merge. So the common sense within the astronomers is that the galaxies will merge, while the center or the central massive black hole will also merge with the merger of galaxies. However, exactly how this process is still an open question because there are so many uncertainties within. So in order to predict how many such massive black hole mergers can be detected by TianQin, we have gathered a large number of different models and then see how many of them can be detected. The number shown here is encouraging in the sense that especially for a subset of these models, heavy seed models, a large fraction of them will be detected by TianQin, meaning that every single event happening in our galaxy, in our universe, will be detected by TianQin. And these detections can not only help us to unveil the mystery of the merger history of galaxy and the growth of galaxies. It can also help us to understand some fundamental physics, for example, to help us understanding the no-hair theorem by looking at the ring-down signal, or to help us to test the alternative theories of gravity by looking at some specific gravitational theories. Now we have already covered the too small or too big. What about the one small, one big? These systems are called as the extreme mass ratio in spiral. They are ideal laboratories within our universe to test the theory of gravity, because they will go round and round for many, many circles, and even very tiny deviation from the general relativity can be detected by some long time accumulation of observation. And we estimated again the rate as well as the parameter estimation accuracy. The bottom line is that for the intrinsic parameters, which dominates the evolution for the phase, we can pinpoint them very accurately. And we can also use such systems to also perform some test of fundamental physics, including the no-hair theorem test. Now we have mentioned all the individual components. What about let's put the signals together and form a background. And these are called the stochastic gravitational wave background. They can be coming from two different origins, the astronomical sources or the cosmological sources. And all we've covered are astronomical origin SGWBs. They are stochastic, meaning they are noise-like, but they are gravitational waves, so they actually are signal, and they form the background, so they kind of below the noise. And by converting some models we used for the previous individual sources, and we can predict what kind of noise level they can be for the gravitational wave background. And this curve shows that TianQin in the future are expected to see many of these background. And for the cosmological origin, for example, the phase transition, the primordial gravitational wave, or the cosmic string, etc., different models give wildly different predictions on the strength. However, TianQin in the future, once operating, can help us to give very stringent constraints on relevant parameters. And we also discussed the possibility of using TianQin as well as LISA to form a network and then to put constraint on these stochastic wave backgrounds. Now, we've covered in the above different sources of gravitational wave events. What about using these detections to understand the physics, not only the fundamental physics like the theory of gravity, but also the expansion rate of our universe, or the expansion mechanism of our universe? We can use such observations of massive black hole binary mergers or standard massive black hole binary in spirals to help us pinpoint the expansion rate of the universe, the Hubble constant. And our preliminary study shows that the accuracy can reach the level of 1%, helping us to potentially resolve the Hubble tension. So these are the science cases or the science prospects of TianQin once they are operating. But what about how to achieve them? And that relies on some data analysis pipeline. So we have some nice data detected by us, and through this data analysis pipeline, we can put them, we can construct the parameter estimation posterior distribution. And we have made some concrete steps towards the aim. We have implemented some parameter, some data analysis pipeline for the wide dwarf binaries, as well as using some radical new novel tools of the machine learning algorithm towards the EMRI system detections. And they are showing promising prospects. So to sum up, TianQin is a spaceborne gravitational wave mission that can operate to detect gravitational wave in the millihertz range. And we aim to detect a large variety of different sources. And we can do exciting science with these detections like fundamental physics, as well as the expansion rate of the universe. And we are working on the data analysis pipelines towards that aim. And that is the end of my talk. Thank you very much. Please let me know if you have any questions. Please go ahead and contact me. Thank you.